We gaze up at the night sky, a vast and endless ocean of stars. We see planets, galaxies, nebulae painted across the cosmic canvas. We've even found things that defy our everyday understanding of reality. We've discovered black holes, places where gravity is so strong that nothing, not even light, can escape their grasp. They are the universe's ultimate takers, swallowing matter and energy forever. But what if there's an opposite? What if there's something out there that does the exact reverse? Imagine an object that can only give, a fountain of cosmic stuff pouring into our universe. This isn't just a flight of fancy. This is a question that emerges from the very same physics that predicted black holes. It's a cosmic riddle, wrapped in the fabric of space-time itself. Imagine a place where you can never enter, no matter how hard you try. It violently spews out matter and light like a cosmic volcano that never sleeps. This object would be a brilliant, blinding beacon in the cosmos. It would be a source of creation, the antithesis of the black hole's destruction. This theoretical object is called a white hole, and it might just be the universe's biggest, most mind-bending secret. Our journey through the cosmos has always been about pushing the boundaries of what we know. We once thought the Earth was the center of everything. Then we learned we were on a small planet orbiting an average star in a vast galaxy among billions of others. Every time we think we have a handle on the universe, it shows us something new, something stranger. The idea of a white hole challenges our imagination once again. It forces us to ask, is the universe symmetrical? For every action, is there an equal and opposite reaction, not just on Earth but across the entire cosmos? So, come with me. Let's embark on a journey of cosmic discovery. Let's peel back the layers of space-time and explore this incredible possibility. We'll travel back in time to see where this idea came from. We'll explore the strange connection between black holes and their hypothetical twins. We will ask the big questions, the ones that make us feel small but also connected to the grand cosmic ballet. So what exactly is a white hole? Let's break it down. Think of a black hole as a cosmic vacuum cleaner. It pulls everything in. Once something crosses its event horizon, that point of no return, it's gone forever. A white hole is the complete opposite. It's a cosmic fire hose. It shoots everything out. In 1915, Einstein gave us his theory of general relativity. These are the mathematical rules that describe how gravity works. They tell us that massive objects like stars, planets bend and warp the very fabric of space and time around them. This curvature of space-time is what we feel as gravity. It's a beautiful and powerful idea that governs the entire cosmos. A few months after Einstein published his theory, a German physicist named Karl Schwarzschild was serving on the front lines of World War I. In between calculating artillery trajectories, he used Einstein's equations to describe the gravity of a single, non-rotating sphere of mass. He found a solution that was shocking. The equations showed that if you squeezed enough mass into a small enough space, the curvature of space-time would become infinite. It would create a singularity, a point of infinite density, and an event horizon from which nothing could escape. He had just mathematically discovered the black hole. But Schwarzschild's solution had a secret. Like many mathematical equations, it had more than one possible answer. The equations worked perfectly fine if you ran them forward in time, describing an object collapsing into a black hole. But they also worked if you ran them backward in time. What happens when you reverse the collapse of a black hole? You get an explosion. You get an object that expands outward from a singularity. This backward solution described a region of space-time that nothing could enter, only exit. The mathematics had predicted the white hole. For decades, this other solution was treated as a mathematical curiosity. It was a weird quirk of the equations that most physicists thought had no connection to the real world. The idea of a white hole challenges our imagination once again. Are white holes real? And if they are, what would that mean for our understanding of everything we thought we knew about the universe? To really grasp the weirdness of white holes, let's use an analogy. Imagine space-time is a giant map with roads on it. A black hole is like a roundabout with every exit blocked, except for the one that leads to the center. Once you enter this roundabout, you can drive around and around, but you are forced to spiral inward. Eventually, you will reach the center, the singularity. There are no other paths. The roads of space-time are flowing inward, carrying you along. You have no choice but to follow them to your final destination. Now imagine a white hole on the same map. It's another roundabout, but different. All the roads lead away from the center. There are no entrance ramps. If you try to drive toward it, the road beneath you is flowing away faster than your car can drive. You can never reach it. The only cars on these roads started at the very center and are now driving away. A white hole is a one-way street that only leads outward, away from a source you can never, ever visit. This one-way behavior is built into space-time's geometry. It's not about a stronger engine or a faster rocket. The fabric of space and time itself is moving. In a black hole, space-time flows inward like a river plunging over a waterfall. In a white hole, space-time flows outward like the blast from an explosion. This is why light can't escape a black hole. It's like a swimmer fighting a current faster than they can swim. And it's why nothing can enter a white hole. It's like trying to swim into the heart of a geyser. This leads to a fascinating connection: the wormhole. Some physicists, like Einstein and Nathan Rosen, proposed that a black hole and a white hole could be connected. In this model, if you fall into a black hole, you might not be crushed at the singularity. Instead, you might travel through a tunnel in space-time, an Einstein-Rosen bridge or wormhole, and come shooting out of a white hole somewhere else in the universe, or even in another universe entirely. That would make the black hole an entrance and the white hole an exit. A cosmic shortcut, a fantastic yet highly unstable one-way street through the cosmos. The adventure begins now. What would happen if you actually encountered a white hole? Let's imagine you're in your spaceship, exploring a distant corner of the galaxy. Suddenly you see it, a point of unimaginable brightness. It's not a star, it's too intense, too chaotic. As you get closer, you realize that asteroids gaslight. This is it, a real-life white hole. Your first problem would be the sheer violence of the environment. You'd be bombarded by high-energy particles, radiation being ejected at incredible speeds. It would be like trying to fly your spaceship into the heart of a supernova. Let's say you could survive the onslaught. What would happen if you tried to enter it? You would fire your engines, pushing with all your might toward the shimmering event horizon. But it would be useless. The fabric of space-time itself is rushing out of the white hole, carrying you with it. The closer you get, the faster that outward flow becomes. No matter how much energy you expend, you would be pushed away. It would be like running on a treadmill that keeps speeding up the harder you run. You would make no progress. The white hole would remain forever inaccessible. From a safe distance, watching a white hole would be the greatest show in the cosmos. What would you see coming out? Primordial hydrogen from the dawn of time, the remnants of a star that fell into a black hole in another universe, a fully formed teacup, a copy of yesterday's newspaper. According to the theory, you could see anything. Because a white hole's singularity is in the past, the things that emerge don't have to follow the rules of cause and effect as we know them, they just appear. This is the ultimate paradox of the white hole. It is an object that is fundamentally observable, it's blindingly bright, but it is also fundamentally unknowable. You can see what comes out, but you can never know where it came from or what the source is like. Any object that emerged would have a history that began at the singularity. It would be an object with no past in our universe, a true cosmic orphan. What do today's scientists think about all this? The idea of a white hole has had a complicated history. For a long time, most physicists dismissed them. They were seen as a mathematical artifact, a solution to Einstein's equations that didn't apply to our real universe. The famous physicist Stephen Hawking, who did groundbreaking work on black holes, was initially skeptical. He argued the conditions needed to form a white hole were too perfect, too unstable. Any tiny disturbance, even a single particle of light, would cause it to collapse into a black hole. However, the conversation has started to change. Some physicists, like Carlo Rovelli, have proposed bold new ideas. He suggests black holes might not live forever. According to quantum mechanics, information can never be truly destroyed. So what happens to all the information that falls into a black hole? Rovelli and others propose that when a black hole completely evaporates through Hawking radiation, it might rebound. In its final moments, it could transform into a white hole, releasing all the information it ever swallowed back into the universe. This idea, part of a theory called loop quantum gravity, provides a possible life cycle for black holes. It solves the information paradox and gives white holes a plausible origin story. Not primordial objects from the beginning of time, but distant future endpoints of black holes that exist today. The echoes of dead stars finally returning what they took. Tiny, ancient black holes that formed in the early universe might be exploding as white holes right now, creating mysterious bursts of energy that astronomers are still trying to explain. Other scientists have wondered if the Big Bang itself was a kind of white hole. The Big Bang, the entire observable universe erupted from a single, incredibly hot, dense point. Nothing existed before it. Everything we see today came from it. This sounds remarkably like the definition of a white hole. Perhaps our entire universe is the result of matter ejected from a supermassive white hole. A mind-bending idea connecting the largest event in our history to one of the strangest objects in theoretical physics. Despite these exciting new ideas, we have to face a cosmic reality. We have never seen a white hole. We have found thousands of black holes. We have taken pictures of their event horizons. We have detected the gravitational waves they create when they collide. Black holes are a confirmed part of our cosmic neighborhood. They are real. White holes, on the other hand, remain completely hypothetical. There is no observational evidence that they exist, so why might our universe have one without the other? The main reason comes down to stability. The mathematical white hole is a perfect, pristine solution. It requires a universe with no other matter in it. In our real, messy universe, things are not so perfect. The theory suggests that a white hole is incredibly unstable. As it spews matter and energy outward, that very same matter and energy would fall back onto it due to gravity. The slightest bit of matter falling back toward the white hole's event horizon could cause it to collapse instantly. It would be like a soap bubble that pops the moment it touches anything. Another problem is how they would form. A massive star runs out of fuel. Its core collapses under its own immense gravity. This process happens all the time across the universe, but what process creates a white hole? The classic white hole solution requires it to have existed for all of eternity, constantly spewing matter. Or, as in the Big Bang theory, it would have to be the origin point of everything. We have no known physical process that would create a white hole in the universe today. This lack of a formation mechanism is a major hurdle. Physics is all about processes, about how things get from A to B. If there's no way to get to B, then perhaps B doesn't exist. This is why many physicists remain skeptical. Unless a new theory like the black hole rebound idea can provide a concrete and testable way for white holes to form, they will likely remain in the realm of fascinating mathematics. The universe might simply not be symmetrical in this one beautiful way. Sometimes nature just picks a favorite. We stand at a crossroads in our understanding of the cosmos.